1.2 Lesson 1, Rate of Change by Equation, Graph, or Table. Our objective for today is, given a graph that shows y as a function of x, you'll be able to estimate the instantaneous rate of change of y with respect to x at a particular value. Vocabulary: average rate of change, secant line, slope of secant line, limiting value, instantaneous rate of change, tangent line, slope of tangent line, derivative. In fact, you've seen an example of this when you did your homework problem that was the extension of number 1 last night. So we have this problem about the pendulum, where d represents the distance the pendulum is from one wall of the room, measured in centimeters, since it was set in motion, represented by t, and t is measured in seconds. So sketch the graph of d from t is equal to 4.9 to t is equal to 5.2. Plot the points 5, d of 5, 5.1, d of 5.1. Find the slope of the secant line passing through these 2 points. How is this related to the average rate of change of d from t is equal to 5 to t is equal to 5.1? What we have here is the graph of the function d is equal to 80 plus 30 times cosine of pi over 3t, where t represents time in seconds and d represents the distance in centimeters from one wall of the room, graphed on the window settings from t is equal to 4.9 to t is equal to 5.2. And the distance varies from, you can see, about a little more than 92 centimeters to a little more than 100 centimeters from that wall of the room. So plot the points 5d of 5. So here is 5d of 5. And 5.1 d of 5.1. So here is 5.1 d of 5.1. So those are the 2 points that we were supposed to plot in number 2 of the extension. Find the slope of the secant line passing through these 2 points. How is this related to the average rate of change of d from t is equal to 5 to t is equal to 5.1? Well, how would you find the average rate of change? You use this formula. You would find the change in distance. So you would do d of 5.1, which would be measured in centimeters, minus d of 5. How far was the pendulum from the wall at 5.1 seconds? And subtract from that the distance the pendulum was from the wall at 5 seconds. So that would be measured in centimeters. So that's the change in distance from the wall. Divide that by the change in time, which would be measured in seconds. So this is the average rate of change of the distance the pendulum is from the wall with respect to time, on the time interval from 5.1 to 5 seconds. If you look at this, this is the change in y divided by the change in x. Or you can say the change in d divided by the change in t, but it's the same thing. So this is actually the slope of the line passing through these 2 points. So the average rate of change is equal to the slope of the secant line passing through these 2 points. In part 3 of the extension, it says write an equation for the line passing through the 2 points from part 2. Graph the function d is equal to 80 plus 30 times cosine of pi over 3t, and the line passing through the 2 points from number 2 on the same set of axes. You may use a graphing calculator. So in fact, you see here the original graph of the function d, which is in red, and the blue graph, which is the graph of the secant line passing through the 2 points d of 5, and 5 d of 5, and 5.1 d of 5.1. and we were able to find the equation of that secant line by first using the slope of the secant line, which is of course equal to the average rate of change of d from t is equal to 5 to t is equal to 5.1, and then we used one point that was on the secant line. We used this point, 5 d of 5, or 595. This is the work that we did, first to find the average rate of change, which was the slope of the secant line, and then we used one point and the known slope and slope-intercept form to solve for the y-intercept, and this is the equation of the secant line. And we have that here, and that's graphed in blue here. So to summarize, what we learned from the extension is that when we find the average rate of change of one quantity with respect to another, we're finding, in fact, the slope of a secant line through 2 points on the graph of the original function. So now we go back to our vocabulary. The average rate of change is given by the slope of the secant line through 2 points on the graph of the original function. Secant means to cut. So you have a line that cuts through the original graph by passing through 2 points. So yesterday we were concerned with approximating an instantaneous rate of change, and yesterday's lesson went over the idea that you can approximate an instantaneous rate of change by calculating an average rate of change over a very short interval of time. So we now know that the average rate of change is given by the slope of a secant line through 2 points. So if you make those 2 points closer and closer to each other, that means the time interval is getting smaller and smaller, becoming more of an instant in time. So the limiting value of the slopes of the secant lines as the 2 points approach each other will give us the slope of the tangent line. So we're talking about something called the tangent line, and basically we define the slope of the tangent line to be the limiting value of the slopes of the secant lines as the 2 points for the secant line get closer and closer to each other. That would be the slope of the tangent line, and when the 2 points on the secant line get closer and closer to each other, that means the time interval is getting shorter and shorter and shorter, becoming more of an instant in time. So to approximate the instantaneous rate of change, you can find the limiting value of the slopes of the secant lines as the 2 points for the secant line get closer and closer to each other. In other words, as the time interval gets shorter and shorter, our average rate of change becomes a good approximation for the instantaneous rate of change. And we call the instantaneous rate of change the derivative of the dependent variable with respect to the independent variable. Now we'd like to take a look at another example for this objective. Given a graph that shows y as a function of x, you will be able to estimate the instantaneous rate of change of y with respect to x at a particular value. So here we have example 2, and it says here in figure 1-2b, which is this figure here, this shows the graph of a function that could represent the height in feet of a soccer ball above the ground as a function of time t in seconds since it was kicked into the air. So somebody kicks a soccer ball and it goes really high into the air and it comes down and hits the ground a little after 7 seconds. So it says here, estimate the instantaneous rate of change of the height at t is equal to 5. So if you look at the graph here we have t is equal to 5, and basically we want to know what's going on with the height of the ball at that time. Is it falling? Is it rising? Is the height increasing, meaning the ball is still rising? Or is the height decreasing, which means the ball is falling? And at what rate is that happening? And part B says, give the mathematical name of this instantaneous rate and state why the rate is negative. Consider this. So we have this point here, which has coordinates 5 for time, and it looks like the height at that time is 60 feet. And let's consider another point that's on the graph, maybe around here. It looks like the time there is 7 seconds, and the height at that time would be, it looks like about 10 feet. So if you want to find the slope of this secant line, the slope of this secant line would be the change in the y coordinates, 10 minus 60, divided by the change in time, 7 minus 5. So the change in the y coordinates represents a change in height, and the change in the x coordinates represents a change in time, which is measured in seconds. So you can see that the ball is falling, so the change in height is a negative value. 10 minus 60 is negative 50, which means during those 2 seconds, from 5 to 7 seconds, 7 minus 5 is 2, the ball fell a total of about 50 feet. So the average rate of change on that time interval of 2 seconds is about negative 25 feet per second. That's the average rate of change. And that is, of course, as we learned from the extension problem from last night's homework, it is the same as the slope of the red secant line that you see there. And as we discussed in reference to the homework problem from last night, we can get an approximation for the instantaneous rate of change of the height of the ball at time is equal to 5 seconds by considering the limiting value of the slopes of the secant lines as the second point for your secant line gets closer and closer to the first point for the secant line. The effect that has is that the time interval becomes shorter and shorter. With these 2 points, the time interval is 2 seconds. But if I, for example, consider maybe this point here, where time would be 6 seconds and the height would be 40 seconds, and then I find the slope of this secant line, the green secant line, that would also give me an average rate of change. And the average rate of change would be, you would subtract the y coordinates of the 2 points. You would have 40 minus 60, and that would be measured in feet. And you would divide that by the change in time. 6 minus 5, which would be 1 second. So in that time interval of 1 second, how much did the height change? 40 minus 60 is negative 20. So that means the ball fell by 20 feet in 1 second. So the average rate of change of the height of the ball on that 1 second time interval is about negative 20 feet per second. And you can see that's a little bit different from the average rate of change of the height of the ball on the time interval from 5 to 7 seconds. If I had to choose one of these as an approximation for the instantaneous rate of change of the height of the ball at t is equal to 5 seconds, I would choose this one as my approximation because it is over a shorter interval of time compared to the first calculation, which was over a 2 second time interval. This one is over a 1 second time interval, and 1 second is closer to an instant in time than 2 seconds. So that's what we mean by saying that we can approximate the instantaneous rate of change of one quantity with respect to another by using the slope of a secant line, and the closer the 2 points are on the secant line, the better the approximation will be. So we say that the instantaneous rate of change is the limiting value of the slopes of the secant lines as the 2 points get closer and closer to each other. So going back to our vocabulary, we see that the slope of the secant line gives us the average rate of change of one quantity with respect to another. And when we move the 2 points on the secant line closer to each other, the slopes of the secant line start to approach a particular value. And that would give us the slope of what we call the tangent line. The slope of the tangent line is defined to be the limiting value of the slopes of the secant lines as the 2 points get closer and closer to each other, and that is going to give us what we call the instantaneous rate of change, which we also call the derivative. So you can see that the average rate of change of the height with respect to time at t is equal to, on the time interval from t is equal to 5 to t is equal to 6 seconds is about negative 20 feet per second. And this would be a reasonable approximation for the instantaneous rate of change of the height of the ball with respect to time at t is equal to 5 seconds. And if you could move the second point even closer to the first point, then you would get an even better approximation. The slope of what we call the tangent line is in fact the limiting value of the slopes of the secant lines as the second point on the secant line approaches the point t is equal to 5 and y or h is equal to 60 feet. So when the second point approaches the first point, the secant line starts to approach the tangent line, and we can use the limiting value of the slopes of the secant lines as our slope for the tangent line. And the slope of the tangent line would in fact be the instantaneous rate of change of the height of the ball with respect to time. So we expect that to be maybe somewhat around negative 20 feet per second. Around negative 20 feet per second. So what we're doing in figure 1-2C is we're taking our secant lines that we drew earlier, and we drew 2 of them earlier, and we're just thinking, okay, if I move the second point closer and closer to the point 560, the secant lines will start to approach what we call the tangent line. So the way you sketch the tangent line is you would just imagine what would happen if the second point on your secant line just moves closer and closer to the first point. And the slope of this tangent line would be the instantaneous rate of change of the height of the ball with respect to time. So you would visually approximate the tangent line, and then you would find the slope of that tangent line just by using 2 points that are on your tangent line. So for example, here's 1 point on the tangent line, and you can see that there's another point on the tangent line, and you're just visually approximating how much of a change there is in height. So there's been a drop of about 56 feet as we go from this point on the tangent line to a second point on the tangent line. This second point on the tangent line is obviously not on the graph of the function. The graph of the function is a parabola, which is right here. So we're just finding the slope of the tangent line. So we're using 1 point that's on the tangent line and on the graph, on the parabola, and another point that's on the tangent line but not on the parabola, just to find the slope of the tangent line. So between these 2 points on the tangent line, there's been a drop of 56 feet, and we've gone to the right by 4 units. So horizontal units are in measurements of time. Vertical, the units for the vertical axis are measurement of distance. So we're going to have an instantaneous rate of change. Instantaneous rate of change and that's going to be negative 56 feet divided by 4 seconds. That's going to be negative 14 feet per second. So that is what we believe to be the instantaneous rate of change of the height of the ball at time is equal to 5 seconds. So going back to the problem, it says this figure here shows the graph of a function that could represent the height in feet of a soccer ball above the ground as a function of time, t in seconds since it was kicked into the air. Estimate the instantaneous rate of change of the height at t is equal to 5, and we just estimated that instantaneous rate of change to be negative 14 feet per second. Give the mathematical name of this instantaneous rate and state why the rate is negative. This is called the derivative. It's the derivative of the height with respect to time. It's the derivative of the height with respect to time, and it tells us the rate at which the ball is falling at a particular instant in time. It's called the derivative. And why is this rate negative? The ball is falling at that point in time, and that's why the rate is negative. Also, from the slopes that we calculated, we can see that as time went forward, the heights were falling. So that's why we see that there is a negative rate of change, showing that the ball is falling. So today we focused on rate of change by graph, tying it back to our extension problem from last night's homework. Given a graph that shows y as a function of x, you will be able to estimate the instantaneous rate of change of y with respect to x at a particular value by, what did we do for our example 2 today? We looked at the slope of the tangent line to the graph at a particular point in time, and that gave us the instantaneous rate of change.